Hey everyone. So at the time of recording this, I do not know if we are going to be in person. If so, then we're going to be taking the free response. If we are not in person, if we are distance, then you're watching this video. Um, I guess I didn't have to say that. I could have just said we're distance, but whatever. So instead of just sitting around waiting for another day, um, the free response is going to be given whenever we get back in person. I'm going to start moving on slightly, a little bit into thermodynamics. Uh, Today, I just want to barely go over the little bit of the first unit. There's not a whole lot there, but the one other thing I want to do is kind of go over the entire unit, what thermodynamics is all about, what are some things to be thinking about in the future. Um, yeah. All right, let's get to it. So, this comes from the AP website. If you ever wonder where I'm getting these, you have access to this. So, if you're wanting more of this information. All right, so there are nine different topics here within Unit 6, thermodynamics. So first, let's just talk about the word thermodynamics. Thermo, you can imagine, is temperature, and then dynamics is like change. Things that are dynamics means like change in something. Um, so, or movement. Dynamics is like movement. So where is thermo, the temperature, moving from one place to another? That's really what's going on here. Temperature, remember, is how much motion is going on the molecular basis, how much they're vibrating or moving or spinning. That's temperature. And in particular, it's kinetic energy. So when we say temperature moving from one place to another, what we're really saying is energy moving from one place to another. All right, and we've already talked about this a little bit when we talked about endothermic and exothermic processes. Notice I say processes, not reactions. We'll get into that later. So we've talked about that already. If basically exothermic is when everything's are exiting, endothermic is when energy is entering the reaction. We've learned a little bit about energy diagrams, but we're going to get into the nitty gritty there. Think about materials like, you can kind of figure this out. Some materials can take on heat very quickly and give heat pretty quickly. Others take a lot to actually heat up and a lot to stay hot for a long time. So we're going to talk about the whys and hows of that. Calorimetry is how we measure this. Energy of phase changes. So going from a solid to a liquid, there's an energy change going on. A lot of this is going to be some math. The great phase change problems. There's some really, it's a classic example of energy going, like you have the question usually goes something like, I have 100 grams of ice at negative 30 degrees Celsius. How much energy does it take to make steam at 120 degrees Celsius? Go. And then you need to figure out how much energy it takes to actually do that. The problem is that you figure out how much energy it takes to raise ice to zero, and then how much energy it takes to melt the ice at 0 to 0 degree ice to 0 degree liquid, and then liquid to 100 degrees, and then turning 100 degree liquid to 100 degree gas. That's another problem. And then finally, turning 100 degree gas to 120 degree gas is another little problem. It's not bad. It's just steps. Just like 3 steps. You have to do 3 separate problems. They're fun. I like them. All right. Introduction to enthalpy of the reaction. So you may have noticed Sometimes on exams, they'll give you a reaction and they'll say delta H equals negative 50 kilojoules. That's what we're talking about. Enthalpy is the temperature change, the energy change, like that. Bond enthalpies. So how much energy does it take to make and break bonds? This is one way that we can calculate the enthalpy of the reaction. Is we know it takes a certain amount of energy to break a bond. Or to make a bond, and we know that if we break the bond, we're going to get back a certain amount of energy. So that is something we're going to talk about. We're going to talk about the enthalpy of formation. This is kind of an offshoot or a continuation of bond enthalpy. Enthalpy of formation basically means if I have raw elements, if I have oxygen and nitrogen, how much does it take to make NO2? And there's a big table that you can look up all these enthalpy of formations. And since we know enthalpy of formations, we can kind of use all of these reactions. And then once we have all these enthalpy of formations, we can use a bunch of these, combine them together, just like we combined elementary steps to make an overall reaction, combine them using something called Hess's law. This unit I consider to be pretty straightforward. Thermo is something that a lot of people actually enjoy. People really, they've said, I wish everything was just Hess's law. This is this is kind of the pinnacle of Thermo. So it's this really isn't that bad. All right, so let's get into it. I'm just going to talk a little bit about this real quick. Chemical thermodynamics. So enthalpy. Enthalpy is the word we use when we're talking about the change of thermal energy in a chemical reaction. So if we say something is exothermic, then that's something that is releasing energy, like this little guy here. This is definitely releasing energy. A match releases energy when you strike it. This means that energy is exiting the reaction. And an endothermic reaction is something that absorbs energy. It gets colder. And this is energy entering the reaction. That's how we go about talking about it. And we've seen a lot of these diagrams in the past. I mean, I'm sure you guys remember this little guy, right? Where the bond of this oxygen and hydrogen are far apart over here, and down here it's just right, but if they get too close, that's potential energy is high. Everything wants to go down as low as they can. That's kind of the general trend of things. They want to be down on any type of energy diagram. Okay? So if we were to go through and draw an energy diagram for endothermic and exothermic reactions, we see an endothermic reaction. We see a positive enthalpy. Positive enthalpy means that we're going up. This reaction is gaining energy. It's absorbing energy. It's entering the reaction. So this means that the delta H, or the enthalpy of this reaction, is positive. This is going to be a positive enthalpy. Okay, endothermic. So again, endothermic, entering the reaction, it's absorbing energy, it's gaining energy, it's positive enthalpy, which means that it's going up on an energy diagram. Okay, and then we have exothermic reactions. Exothermic reactions is the opposite. It's where the energy is exiting the reaction. Energy is being lost by the reaction. So that means we have a negative delta H, and that means it's going down on a energy diagram. Okay, so that's all I really wanted to talk about today, is just this idea of what is enthalpy. We denote it as delta H. If we say something has a positive enthalpy, it means the reaction is gaining energy. Energy is entering the reaction, and it's endothermic. And then the opposite for exo. One thing that we've talked about, and I want to ask you, is which one of these guys do you think is going to just happen? What we call spontaneous. Which one is going to just spontaneously happen without really any need for outside influence? Remember, everything wants to be down. So if this reaction is kind of going to a more unstable spot, it's going to a more highly energetic spot, this is not going to be spontaneous. We're gonna have to put work in to do this. This reaction, though, everything wants to head down, so this can just move forward without us putting a whole bunch of work into it. So that's what's going on here. All right, guys, that's it for now. Short little video. Like I said, free response is going to be next time I see you guys in person. So we'll see you then. Have a good one, guys.